Okay, let's dive straight in. We're looking at a really interesting paper today called SPICY. Self-play in corpus environments improves reasoning. If you're watching how large language models are learning to, well, learn better on their own, this one's a big deal.
It really is. I mean, the headline finding is pretty stark.
Yeah.
The older ways of doing self-play, they basically hit a ceiling. They stagnate.
Right.
SPICY proposes a different approach. It's still self-play using reinforcement learning, but here's the twist. One model, two jobs. It acts as both a challenger and a reasoner.
And the absolute key, the game changer, seems to be grounding it all in real-world text, verifiable knowledge.
Exactly. The challenger digs up tasks, novel ones, from this huge pile of documents, verifiable tasks.
Well, the reasoner has to solve them without seeing those documents. That gap, that information asymmetry, that's the engine driving improvement, right?
That's precisely it. And because it's grounded in this external corpus, the improvement doesn't just fizzle out, it keeps going.
And the results they're showing aren't trivial.
No way. We're talking significant jumps. Like plus 8.9% absolute gain in math reasoning, plus 9.8% in general reasoning benchmarks.
Wow.
And look at the Qwen 3-4B base model that saw a huge plus 9.1% absolute gain just from this method, training on its own self-generated but crucially fact-checked questions.
Okay, that definitely sets the stage.
Okay.
So we're talking about breaking through LLM stagnation. Let's unpack the why first.
Yeah.
Why did the original idea of self-play, which works so well in games like Go, sort of fall flat for LLMs on their own?
Yeah, it's a fundamental difference. In games, you have clear rules, an objective environment. An LLM trying to teach itself using only its own thoughts. It runs into, well, basically two killer problems.
The first one they flag is hallucination amplification. Sounds bad.
It is bad. Imagine the model makes up a question and an answer. If that answer has even a tiny factual error,
Which LLMs are prone to do.
right, then the model trains on that error, and because it's all internal, a closed loop, the next time it generates something, that error gets reinforced, maybe even magnified.
Huh.
It snowballs. The model gets really good at being confidently wrong because there's no external reality check.
Like practicing a typo over and over until it feels right. Okay, that makes sense. But the second issue, information symmetry, feels, I don't know, deeper, like it limits the potential for growth.
I think it does. Information symmetry just means the part of the model generating the problem knows exactly the same stuff as the part trying to solve it. It's the same underlying knowledge.
So it can't really surprise itself.
Pretty much. How can it create a genuinely new, challenging problem that pushes beyond what it already internally represents? It can't, really.
So you end up with problems that just test the edges of what it learned during pre-training. It gets repetitive, maybe simpler over time.
Exactly that. The difficulty stalls out. The problems aren't pushing the boundaries anymore. And that's where SPICY comes in. It breaks that internal loop, forces interaction with that big external document corpus, D.
Okay.
That gives you novelty, diversity, and crucially verifiable truth. It shatters the symmetry.
Let's get into the nuts and bolts then. How does SPICY actually make one model wear these two hats, challenger and reasoner, and keep their knowledge separate when it counts?
So the challenger, C, is like the teacher creating the assignments. First step, pretty straightforward. It just grabs a random chunk of text, a passage, from that huge corpus D, could be up to, nearly 6,000 tokens?
Just raw text.
Raw, unstructured text. Then its job is to read that passage and generate two things. A tough question Q and the correct answer, a star, pulled directly from that text.
And you mentioned diversity. It's not just asking what is X.
No, and that's super important for general reasoning ability. It can generate multiple choice questions, MCQs, or freeform questions, and the freeform answers can be numbers, math expressions, strings, lists, even true-false.
So it's flexible.
Very flexible. This stops the model just learning tricks for one specific question type. And the absolutely critical part, because a star comes straight from the document, it's grounded, in fact. No hallucinated answers sneak into the training data.
Okay, challenger makes the fact-checked quiz. Now, the reasoner, R, this is where the tension comes in, you said.
Yeah, because the reasoner only gets the question Q. It never sees the source document that the challenger used.
Total information hiding.
Total hiding. It's forced to rely purely on its own internalized knowledge and reasoning skills. It's prompted to think step by step, show its work.
Like in math class.
Exactly. And then it has to put its final answer, let's call it a hat, inside special tags, like a box.
Boxed.
It just makes it easy for the system to automatically find the final answer. Then a simple verifier, maybe rule-based like math verify or just checking if the strings match, compares the reasoner's answer, a hat, to the challenger's gold answer, a star.
Okay, so Challenger makes verifiable tasks from documents. Reasoner solves them blind. But how does the system learn what a good task is? How does the Challenger get better at challenging? That sounds like the RL part.
That's the core of it. The reasoner's reward, RR, is dead simple. 1 if it's right, 0 if it's wrong.
Really?
Easy.
That's...
But the challenger's reward, RC, that's where the magic is. They call it the variance-based curriculum.
Okay, variance-based. Why variance? Why is that the secret sauce here compared to just rewarding difficulty?
It comes down to learning theory, really. What's the optimal point for learning? Not too easy, not too hard.
The Goldilocks zone.
Exactly. The reward function they design is shaped like a bell curve, a Gaussian. It peaks, hits its maximum value of 1.0 only when the reasoner gets the question right exactly 50% of the time, on average.
50%, not higher.
50%. If the task is too easy, say the reasoner gets it right 90% of the time, the reward drops. Too hard, maybe only 10% success, reward drops again. They calculate this based on the variance across, I think, K8 attempts by the reasoner on that single question.
Huh. That is clever. Because if you give me something I ace every time, I'm not learning. If I fail every time, I just give up or guess randomly.
Precisely. That 50% success rate marks the very edge, the frontier of what the reasoner can currently do. So the challenger is constantly incentivized, rewarded for finding questions right at that edge. Difficult, but solvable.
Pushing the boundary.
Constantly pushing it. It creates this automatic curriculum that gets harder as the reasoner gets smarter. It self-tunes.
And this leads to that coevolution you mentioned. It's not just the reasoner improving, the challenger is actively getting better at its job, too.
Yes, and they showed this empirically. It's pretty cool. During training, the challenger demonstrably learns to make harder problems. If you take a snapshot of the reasoner early on and test it against problems generated later by the challenger, its success rate drops significantly, from like 55% down to 35%. The questions are genuinely getting tougher.
While at the same time.
Well, at the same time, the reasoner itself is getting much better. If you test the evolving reasoner on a fixed set of problems, its success rate skyrockets, from around 55% up to 85%.
Wow, okay. So both are learning, pushing each other.
Exactly, they're learning together. The paper mentions using a specific RL algorithm, Dr. GRPO, which helps manage this complex setup where they share model weights that need separate learning signals for each role. Ensures the updates are meaningful.
Okay, the mechanism sounds solid. But the proof is in the pudding, right? Let's talk ablations. These are the experiments where they take things away to see what really matters. What happens if you take away the corpus grounding?
That was ablation 1. Crucial test. They ran SPICY without letting the challenger access the external documents, basically forcing it back into that closed loop like older methods.
And the result?
Performance dropped. The overall average score was 3.2 percentage points lower without the corpus, went from 43.9% down to 40.7%. It's strong evidence for their main claim. You need that constant stream of new, verifiable information from the outside world to keep improving, to avoid stagnating.
Makes sense. What about the coevolution part? Did they try just having a static set of hard questions, a fixed challenger?
They did, ablation 2. Compared SPICE against a baseline where the challenger didn't learn or adapt. The reasoner still improved, but much, much more slowly. It confirms that you need the challenger to keep raising the bar. If the tasks become too easy because the reasoner has outgrown them, the learning slows right down. That adaptive difficulty, that adversarial push, is key.
So the variance reward really matters. Did they compare it directly to other reward ideas?
Yep, ablation 3. They tested the variance reward against older strategies. Things like rewarding just getting the answer wrong, absolute 0, or the R0 approach, or a simple threshold like try to keep failure rate above X%.
And SPICY's variance approach won out.
Clearly. It got the best average performance overall, 44.9%. It really backs up the idea that learning is fastest right at that 50% sweet spot, not just maximizing raw difficulty or failure rate.
Okay, and quickly, the last couple of ablations, corpus type and task type. Anything jump out there?
Yeah, 2 quick things. 1, mixing corpora helped. Combining a math-focused corpus with a general reasoning one gave the best overall result. Diversity in sources is good.
Unsurprising, perhaps.
And 2, mixing task types, MCQs, and freeform was also better than just one type. MCQs are easy to verify reliably, which is great. But the freeform questions seemed especially good at pushing deeper reasoning, particularly in math. The freeform setup alone got the highest math average score, 52.5%.
Suggests that having to generate the steps, not just pick an answer, forces more robust learning.
That's the likely interpretation, yeah. It pushes beyond simple pattern matching.
Okay, numbers are one thing, but you mentioned seeing the quality of reasoning change. That solar eclipse example sounds fascinating.
It really brings it to life. So imagine the challenger is looking at a document passage about the moon, sun, distances, diameters, basic astronomy stuff.
Right.
Early in training, maybe step 50, the challenger asks a super simple question from that text. What's the moon's diameter? Answer, 3,475 kilometers. Just basic information retrieval.
Easy lookup.
Trivial. But much later in training, using the exact same document passage, the challenger creates a way more complex task.
Like what?
It described an alien civilization on another planet observing their own star being eclipsed by their moon. It asks the reasoner to figure out the distance to the alien star, given its diameter, and the fact that the angular size ratio, diameter over distance, is the same as for Earth, Sun, and Moon during an eclipse.
Whoa, okay. That's not a lookup. That requires understanding the relationship, setting up a proportion.
Exactly. Multi-step proportional reasoning. And the reasoner's attempts show this learning curve beautifully. Early on, faced with that hard question, the reasoner might just guess wildly, like, stars are much further than moons, maybe 1,000 times, just intuition, no real logic.
Right, a stab in the dark.
But later in training, the reasoner's output is totally different. It actually writes out the principle. Diameter divided by distance is constant. It sets up the equation, moon diameter, moon distance equals star diameter, star distance. Then it plugs in the numbers and solves for the unknown star distance step by step.
That's actual reasoning being developed.
Yeah.
Not just memorizing facts, but learning a procedure.
It's genuine development of reasoning skill. Yeah. It's learned how to tackle that type of problem, not just that specific instance.
So, wrapping this up then, SPICE-E feels like a really significant step. It tackles those core problems of self-play in LLMs, the hallucination loops, the information symmetry dead ends.
Right. It replaces that flawed internal introspection with this open-ended, verifiable learning process driven by external knowledge.
Anchored in real documents.
Exactly. And if you, listening to this, are thinking about how we scale AI capabilities, SPICE-E offers a powerful potential pathway.
How so?
Well, think about it. It achieves these pretty impressive reasoning gains using only unstructured documents, stuff we have tons of, and self-supervision. No massive human labeling effort needed for the curriculum itself.
That's a crucial point.
So here's the provocative thought. What does this mean for fields where getting high-quality human expert data is really hard or expensive? Specialized science, engineering, medicine. Could a SPICE-E-like approach allow models to bootstrap expert-level reasoning in totally new domains just by reading the available literature and teaching themselves? It potentially changes the game for scaling expertise.